One of the most remarkable facts from Calc 1 is the fundamental theorem of calculus. And what the fundamental theorem said is that if you've got the integral on an interval from a to b of f of x dx, this is equal to big F of b minus big F of a, where the derivative of big F is little f. So this just says that rather than going through the long convoluted Riemann sum process for this integral, we can instead find the antiderivative and evaluate the antiderivative at the endpoints. So we've got something similar for line integrals, and this is creatively enough called the fundamental theorem of line integrals. And this statement is somewhat similar. If you've got an integral along a curve of this vector line integral f dot dr, this is equal to f of b minus f of a, where the gradient of big F equals little f. So here, back in the one-dimensional case, big F was called the antiderivative. So you can think of big F here like the anti-gradient, although we don't use that terminology. That this big F is called a potential function for F. So potential, think of that like anti-gradient. So, the first thing to note is that not every vector field has a potential function. Let's look at an example of a vector field that doesn't. So this is a sort of non-example. Let's say we have f of xy is equal to xy. So to determine whether or not this has a potential function, well, suppose it does. If this has a potential function, that means that the gradient of that function has got to equal xy. And the gradient of f, well, that means the partial of f with respect to x has to be equal to the first component, and the partial of f with respect to y has to equal the second component. If you just take this pair of equations, if you look at the first one, and if we integrate this with respect to x, this says that f has to be x squared over 2 plus a constant. Now that constant is only constant as far as x is concerned. We only integrated with respect to x. So it could depend on y, on the other variable. If we now plug this into the second equation, we take its partial with respect to y, gives us c prime of y equals xy. Well, c was constant as far as x is concerned. So that means its derivative is also. So this function does not have any x's in it, but it's equal to x times y. So that gives us a contradiction here. That means that there couldn't have been a potential function. So that f didn't exist in the first place. So a field that has a potential function is called conservative. That's a little bit of terminology that you'll see come up in physics an awful lot. And maybe the next few sections will look more at conservative fields. So, so all this stuff that we're going to talk about in this section really only works if your vector field is conservative, if it has a potential. So how do you test for it? So this is a theorem for determining whether or not a function has a potential. This is called the curl test. Before we get into this, we need to define a few things. So first, remember this right here. This means this is the gradient of f. And this is the partial of f with respect to x, comma, partial of f with respect to y, and so on. So this is the vector of partial derivatives of f. This is the derivative operator we've looked at most in this class up to this point. We've got two related operations. First one is called the divergence, and the divergence applies to a vector field, and it's written as this symbol dot f. Now, if f is a vector field, what this means is think of this gradient symbol as the partial derivative operator, and we're dotting it with the field f. So to do the dot product, you multiply the first components together. So this is the partial of f1 with respect to x plus the partial of f2 with respect to y plus and so on. Now in this section, we're not going to look at dot product, at this divergence yet. But it's one of the three main operations, so I just want to give you the definitions now, and we'll come back to divergence later. And the last one is the curl. And think of this like the same way. This is the partial of f, partial with respect to x, partial with respect to y, partial with respect to z, cross f1, f2, f3. In this course, divergence can be applied to a function of 2 or 3 or 4 of however many variables the vector field has, whereas the curl only applies to a function of 3 variables. If it is a function of only 2 variables, treat it like a constant as far as z is concerned. But it only works in 3 dimensions because this cross product only works in 3D. So this gives us the determinant of, well, our first row are the unit vectors I, j, k. The second row are the entries of the first vector. Those are the partial derivative operators. And the bottom row are the components of the second vector, f1, f2, and f3. So with those definitions here, what the curl test says is that a vector field f is conservative if and only if the curl of f is 0. Let's briefly take a look at why this is. So that's what the curl test says. It just gives you a quick test to see if this is conservative or not. So why this is, well, let's suppose that f has a potential function. So if f is equal to the gradient of some potential, that means that the partial of f with respect to x is equal to f1, and the partial of f with respect to y is equal to f2, and so on. If we take the curl of f, this gives us the determinant of, well, it gives us this matrix right here, I, j, k, the partial with respect to x, partial with respect to y, partial with respect to z. And our bottom row are the entries of f. So they are f1, f2, and f3, but f1 is the partial of f with respect to x. And f2 is the partial of f with respect to y, and f3 is the partial of f with respect to z. If we expand out this determinant here, in the I component, we've got this cross multiplication right here, and this gives us the partial of f with respect to z with respect to y, minus the partial of f with respect to y with respect to z. And then for the j component, likewise, we've got these two. So this is fz with respect to x minus fx with respect to z, plus, and then the k component is this cross multiplication. That's fy with respect to x minus fx with respect to y. And remember what we said before is that we have this established that the order of the partial derivatives doesn't matter. So this is 0, as is this, as is this. So that gives us 0 for our curl. So anytime we've got a conservative vector field, we can use this test to determine that or not. So now that we have this test to see if something is conservative, if it has a potential, how do you actually find the potential? So finding a potential. We saw the basics of this in the first example in this section. Let's look at a full-blown one now. Let's say we've got f of xyz is 1 over x minus cosine x minus y plus yz squared. And then our y component is xz squared plus cosine x minus y plus 2y. And then our z component is 2xyz plus 1 over z. So now if this has a potential function, big F, that means that this right here must be the partial of f with respect to x. And this must be the partial of f with respect to y, and this is the partial of f with respect to z. So let's write that out. So that means that fx equals 1 over x minus cosine x minus y plus yz squared. And then for our y component, we know that fy is equal to xz squared plus cosine of x minus y plus 2y, and the partial of f with respect to z is equal to 2xyz plus 1 over z. So we're going to look at two methods for this. The first is the official method to do this. So the official way to do this is to take the first equation and integrate it with respect to x. So that says that f, I'm going to leave this out a little bit to save some writing, so f must be, we integrate this with respect to x, and we've got ln x minus sine of x minus y plus xyz squared plus a constant. Now this c is only constant as far as x is concerned, so it could depend on y and z. Well, now that we have this, we'll plug this into the second equation. So plugging this in here means we've got to take its partial with respect to y, and taking the partial with respect to y, it's got to equal this stuff. So the partial of this with respect to y is going to be cosine of x minus y plus xz squared plus the partial